Welcome everyone. Welcome to the problem solving session on Introduction to Semiconductor Devices NOC 23E82. For this is week 7 we are meeting on September 9, 2023. My name is Amit. I am a PhD scholar at IISc Bangalore. Just to quickly go through what I've been talking about in this sessions is that in the week 1 we talked about material classification. Primarily we talked about in terms of electrical conductivity, that we can categorize metals, insulators, and semiconductors. We saw some basics of quantum mechanics like de Broglie wavelength, h upon p, Heisenberg uncertainty principle, and we saw some infinite quantum wells. That is, if you draw potential versus position, and if you see something like this is goes to infinity, and we saw that a particle which is here is trapped and it will have a quantized energies. It will not have a continuum of energies but quantized energy. And this is an asymmetric well, that is from 0 to L. We saw symmetric wells which are from minus L to L or minus L by 2 to L by 2. Then we saw peculiar phenomena about the quantum world. That is, again, on the y-axis is your potential, on x-axis is your position. Let's say it's a 1D system, and say some particle is coming with some energy E naught, and this barrier has a V barrier height. Now classically this particle can never cross this, but in quantum mechanical world you can have a finite probability of finding this particle over here. Note, quantum mechanical is a probabilistic world, not a deterministic world. This phenomena is known as the quantum tunneling in a finite quantum well system. And finally we saw that in semiconductors we can just assume that when two particles are coming together, they form they overlap their wave functions. The electrons which are there, they overlap the wave functions. Then we introduce the Ronick-Penny model using periodic potentials. You solve it and you get something called an EK diagram, which is the dispersion relation. So dispersion relation is something called a EK diagram, and in EK diagram what you get is a something called a gap between two states. So this is your first state, below this electrons can reside. This is EV. On top side is your EC, where also electrons can reside, and this is the forbidden gap. So the EG, what we call it, and we notice that electrons cannot reside here. And we also saw these, although I'm drawing these bands to be flat, they are not flat, they have a slight curvature to them, which in turn determines the effective mass, also denoted as M star or M effective. For electrons as well as holes, they are different, and they are dependent on the curvature of EC and EV. So this is EC and this is EV, something like that. And so the double derivative or the curvature determines the effective mass. We saw the formula finally, and so effective mass is a strong tool, in the sense that all the quantum mechanical effects can be condensed to effective mass, and we can continue using the classical mechanics that we have been using. F equal to ma we can directly use, for instance. Finally we saw doping in a semiconductor, that is a semiconductor which does not have any impurities. If you add some donor atoms, they can donate electrons, and the whole semiconductor turns n type. Similarly, if you add some impurities which can accept some electrons, we call them p-type acceptor atoms. So semiconductor is p-type rather. Finally, you saw a very fundamental tool in quantum semiconductor world, which is the Fermi level, which is essentially where the Fermi function is a probabilistic function determined which has basics in quantum mechanics, right? Fermi function, and Fermi level is where you finding the probability of electron is half. We saw its position in the band gap, that if it's a intrinsic semiconductor or undoped semiconductor, it will be directly in the middle. So this EC and EV, for intrinsic semiconductor it will directly in the middle. And we saw that if you dope, the EF will shift towards EV. If you dope it n type, if you dope it p type, the EF will shift towards EV. If you dope it n type, the Fermi level will shift up towards EC. We also saw a non-degenerate semiconductor is, that is, EF should have a distance of 3 kT from EC or EV, depending on whether it's p type or n type. Finally we saw some carrier concentrations, some expressions for them in equilibrium. NC and NV were some constants, NC for your electrons, NV for your the states available. Ni is your intrinsic carrier concentration. For silicon, for instance, a room temperature is 1.5 into 10 to the power 10 cm minus 3. So just to recap, I'm just going through what I've been doing in the previous sessions. We'll come to today's sessions. Finally, we saw carrier concentration depends on temperature. When you have very low temperature, there is very few ionization. Very few dopants that you have added are ionized. So it's it's of there are very few carriers, so we do not use it for many applications. Finally, it's extrinsic regime where the carrier concentration is equal to the dopant concentration. Finally, if you increase the temperature even further, then the bonds of the intrinsic semiconductor start to break, and once that happens, a lot of electrons and holes are generated, a huge amount of supply of electrons and holes, which can contribute to the current. Now, how do these contribute to the current? We'll see in a minute. Just a second, some people are joining. All right, so first, just to so we saw there are two flavors: drift current, that is when the movement of electrons in the presence of an electric field. So we saw some entity called mobility mu, right? And we saw that drift velocity equal to mu times E. This E is external field, or field rather, electric field. Mu is a mobility, Vd is your drift velocity, and conductivity we saw denoted by sigma as Ne nu in terms of electrons. For holes, it would be P. N is the electron concentration, E is the electron charge, mu is its mobility. Finally, the transport can also happen due to diffusion. For instance, there's a large number of electrons in one side of semiconductor, other side there are few electrons. So due to this concentration gradient, the electrons will diffuse. Same can happen with holes, and then total current will be the sum of drift and diffusion. And there's a relation called the Einstein relation, which links the mobility to diffusion coefficient at a certain temperature. Finally, up until this time, we had been talking about at equilibrium. What happens in semiconductor is not a thermal equilibrium. That means we are injecting some carriers by applying a battery, for instance, or you shine light, and a lot of electron and holes can be generated. And naturally, or you might expect that some of them will recombine. So all these things we talked about solve some problems, and the crux of it was summarized in minority carrier diffusion equation in week 3, where we saw that total excess minority charge carriers are a function of drift, diffusion, generation, and recombination. And we all saw this at low level injection. Low level injection means that the external that you are carriers, for instance, you are generating or injecting, are low as compared to the background doping. You can just go through the previous sessions. So what I'll do is that I'll copy paste my YouTube channel link where I upload these weekly sessions, as well as my email ID. Of course, you will have your the group where talk about, you can post your doubts, and the assignments and assignment solutions are also posted. In the next, using all these basic semiconductors, we talked about the p-n junction. That is, on one side you have p-type semiconductor, and the other side it's n. So we bring them together, we saw there is a diffusion and there's a depletion region that is formed. That is, the holes diffuse from left to right, electrons from right to left, and this region is devoid of any mobile charge carriers. No mobile charge carriers, only the dopant ions will remain there in equilibrium, that is. And we saw different flavors, like mostly we were concerned in abrupt p-n junction. We saw some examples of pn plus or p plus, and this means p plus n is moderately doped and p is high doped. Finally, we saw the very fundamental thing in that, depletion approximation, which is used to solve the Poisson's equation. And we also saw what do we mean by quasi-neutral region. Finally, the key terms which we still talk about in today's session are depletion width, electric field, stored charge, and built-in potential. These are the very basics which will I mean, in every device you encounter, these will be brought upon, whether you talk about p-n junction, Schottky junction, MOSFET, everything. These things will keep appearing again and again, so you must be comfortable with them. We talked about quasi-Fermi level, that is when this is not in equilibrium, that is under injection, we are injecting some carriers, electrons and holes. We saw the Fermi level splits, and we invoked something called the quasi-Fermi levels, and I told you this is not under equilibrium. So when we put the p-n junction forward bias, we saw we are injecting some carriers, which causes the potential barrier lowering, and thus the majority carriers can cross the depletion region, where they become minority on the other side, and thus they can recombine. This whole process generates currents. We saw one very famous diagram, the contribution of drift as well as diffusion, the hole as well as hole diffusion, electron drift, and hole drift. And we saw the law of junctions and the reverse saturation current, their expressions. Then we discussed the case of reverse bias, where the depletion region widens as due to the application of reverse bias, and naturally a potential barrier also gets increased. Is anyone facing the same problem? The PPT is blurry. Can someone respond? All right, I'll just unshare and I'll redo it. Okay, just wait a minute. Is it better now or still the same? All right, I'll disconnect. Not disconnect. I'll stop presenting and just try reopening the software. Just give me a minute. Just hold on. Sorry for the problems here. Is it any better now? I reopened the software. I mean the Microsoft presentation software. Am I audible?
So yeah, sir, now it's better, but still there's some blurry. So
All right. Okay. Just let me do one thing. How does it look now?
yeah, sir, it's perfect. Yeah.
Okay. So I think that's the problem with those slides. That slide itself. All right, so I just quickly go through the summary for the last week also. Yeah, so under reverse bias we saw depletion region widening. We also saw an important concept of junction capacitance, that is in that's valid in the reverse bias. In the forward we call it diffusion capacitance, and we saw its dependence on reverse bias and doping. That we also saw when we talked about depletion region. If you recall the depletion region expression, right, it depended on the built-in potential and doping. So same concept is revisited in this capacitance. And we saw one particular problem where we apply such a high reverse bias that among of the two sides, for instance, of this PN junction, let's say this is like that, we apply such a high bias that whole of this gets depleted, reverse bias, that is. So this is reverse bias. So we apply such a high reverse bias that all of this N region gets depleted. And we solved, these are some peculiar things that may happen in your real world devices. Finally, last week we talked about the metal semiconductor junctions. No, previously it was PN junction, so both were semiconductors. Here, the left side is the metal, let's say. So it's metal, and then on this side we have the semiconductor. So again, due to the Fermi level, there can be band alignment and band bending depending on the work function. We saw the work function definition as the energy difference between the vacuum level, some arbitrary vacuum level, with the Fermi level. That's true for metals as well as semiconductors. Metal semiconductor junction is also known as a Schottky junction. We saw some things. These are again some key terms that came again. Barrier height, the built-in potential depletion width came again. Finally, we just logged the PN junction. We saw the current in the Schottky junction. The difference here is that the current is due to thermionic. So thermionic is made of two words, therm plus ionic. This means the ions, in this case electrons and holes, are emitted due to the temperature, not due to some diffusion or injection, but due to temperature. So it has a strong dependence on temperature, which you also saw in the reverse saturation current as well as the researcher's constant. Just go through the lecture slides or the videos for more details. And we saw a quick comparison with the PN junction, and this is the most important facet of it. So for instance, you want to make a Schottky or ohmic contact with semiconductor, you want to measure its current, right? So you must have an ohmic contact. So how to do that? What metal should we choose? We saw one or two examples of that. Rectifying contact is your on. It's very similar to a PN junction, except that it has a low knee voltage and a high reverse saturation current. Finally, and this is where we continue today, we saw something called a metal-oxide-semiconductor capacitors. So I'll just revisit all these concepts for the MOSCAP today, and so let's get started for today. Before that, I'll take a pause, and if you have any doubts regarding the sessions till now, you may ask, and as always, feel free to stop me anytime. I've also shared my email ID so that you can write for some specific doubts. I prefer you write in the forum so that others can also benefit, but if you need some personal attention, you can write. I'll again share the uh, my YouTube channel where I upload the recordings of these sessions that we conduct, as well as my email ID. Okay, so let's get started for today. On your screen you have a MOS capacitor. So as the name suggests, it's a metal oxide semiconductor. So this is your metal, here is your oxide or insulator. Sometimes these are also known as MIS devices, metal insulator, but for silicon usually the insulator is insulator is typically oxide in case of silicon, so hence this is also known as MOS capacitor. And obviously you are on a semiconductor substrate, which is over here. There are some assumptions which we are making because real world complications always arise, so we first make some assumptions and we'll violate them, we'll relax them one by one, not violate them, we'll relax them one by one for a more complicated and we'll closer to a real world. So metal semiconductor Fermi levels are same, so this means you must know this is, let's say, metal, this is the Fermi level of the metal, and on the right side, let's say you have some EC, EV, and depending on how the doping is, it will have EF. And all this is based on some, on the top you have, this is the vacuum level. So everything is measured with respect to this vacuum level, right? So here what I mean that this EF metal and EF semiconductor are the same. They are not the same, but we are assuming them to be same. And there are no traps. This means the insulator is of very good quality. There are on the interface, that is either here on this interface, this perfect interface, or in the bulk here. So there are no traps. This means no charges here or anything. Metal is thick. Usually sometimes the metal is thin. Their electric field is not uniform. So metal is thick enough so that we can assume the metal is equipotential. This is very rarely violated, by the way. Finally, semiconductor thicknesses are larger than the maximum depletion region thickness. I told you we solved a problem. Or you can apply such a high field that whole of semiconductor is depleted. We're not talking about that. The fields are low enough that there is still, so gray region is depleted, for instance, you can assume. This is, let's say, depleted. I just assume that for now. But this white region, it still has some mobile charge carrier, so it's not depleted. Finally, oxide is a perfect insulator. Again, no leakage paths and all. So this is very good quality oxide. That is also, this interface is good. That's our assumption. Fine. So what we have, as we talked about, so on this side also you have an EF, which is not drawn here. Because note, EF metal, we have assumed EF metal and EF semiconductor are the same. This is your metal. The dashed one is your metal, and this side is your semiconductor. This condition is known as a flat band because you can see the bands of semiconductor are flat. So a very non-creative name, but we'll work with that. Then what we do is let's say, okay, so before we do that, since EF is closer to EV, this is EV, this is EC, and this in the black dashed line is your EI. So we know it's a p-type semiconductor. This is a p-type semiconductor on your right. So this is a p-type. All right, so if we apply some let's say some negative voltage, so what's going to happen, obviously some electric field will be taken up by this oxide. Remember, it must have some dielectric constant and some finite thickness. So always just remember that with electric field there is always a potential associated. So whatever electric field it has, some of the potential will drop here, some will drop here. So just forget about the oxide for a second and just assume that if you apply negative potential, there are holes in this, correct, p-type semiconductor, they'll get attracted to this interface. They cannot cross the oxide. Remember, it's a perfect oxide. They'll get accumulated here. And so what will happen at the surface, you see EF is coming closer to EV. Note there, in the bulk there is some distance, but on the surface they are very close. And if you recall an expression, P equal to pi exponential of, or let's say call it nv, exponential of ev minus ef over kt. So what's happening, this is true in every part of this semiconductor. So here evf and ef are coming close, the concentration of holes must rise, hence this is called accumulation. Holes concentration rises, and thus we call this something called accumulation. All right, so what will happen when we apply negative bias? Negative bias, again, just forget about oxide for a second. When you apply positive bias, this positive bias will repel the holes. There are bunch of mobile carriers here, right? This positive potential will tend to repel them, correct? So it repels. What will happen is that it will form a depletion region, because the negative charged ions will be then exposed. So this we have seen, this is called the depletion region. This region will be depletion. Let's call this width w, correct? Holes, again, you can see cannot come this side, so they will have migrated to somewhere over here. Okay, what happens, and notice one key thing, that this is ei. Now bends have bent, and it just so happens that the difference, that the ei at the surface has become exactly equal to ef. So if you apply this expression nv exponential of ev minus ef over kt, so at surface okay, I think I'm doing something wrong here. Just a second. So this is some constant that I think I might be taking this wrong. Okay, so let's anyways, my logic will still stand. So it will be nf. So ev at this junction, at surface, this is what we call the surface, or the interface, metal oxide interface. So this at surface will be, so ev will be somewhere over here, right? And ef is somewhere, so ev minus ef will be directly be equal to your eg by 2, exponential of eg by 2 kt, and this whole thing is nothing but your ni, the intrinsic carrier concentration. So you notice that the bends have bent so much that at the surface it's behaving like an intrinsic semiconductor, correct? Because whole concentration is equal to ni, and naturally the electron concentration will also be ni. What happens if we further increase this bias? If we further increase this bias, you see the bends bend even further, and now at the surface you see ef is closer to ec. This is ec and this is ev. This implies at surface now it's n-type behavior, right? But the bulk is still p-type, and at this interface, oxide semiconductor interface, it's n-type. This is an inversion. Its nature has inverted from p to n. Hence this regime, when ei at the surface, right, we'll see in more details, but this is some, when the nature has become reverse, this is called inversion. And this is the complete basics of a MOSCAP. All the problems and everything can be solved or explained, all the phenomena, if you understand this. All right, and we are going to do that. So just some very basic warm-up problems I have here. So we have to match the band diagrams that are given with the charge distribution. All right, so let's just start with the first one. So you see ef, this is, just look at the bulk, forget about the depletion region for now. Look at the bulk. In the bulk, ef is closer to ev, so I call this means this is a p-type semiconductor. All right, and at the interface you see this interface, we call this oxide and semiconductor interface. What's happening? ef at surface is equal to ei, right? And not so this bends have bent. Why this would have bent? This depletion region will be created when vg is negative. When vg is positive, the holes will be repelled, because this is a p-type semiconductor, and you will form a depletion region. So on this you will see positive q, this is the metal surface, okay? On the metal side, you'll see a plus q. So all the three options have that. But in this depletion region, you will see a slab of negative charge like this, because all the negative ions would be exposed. The holes have been repelled away. You see something called this. So 1 will match with C. And this regime I told you is the depletion regime. So 1C depletion. This is correct. Let's look at 2. Again, this is a p-type semiconductor. Why? Because in bulk, EF is closer to EV. And you see the depletion region has widened even further. You see this, compare with this. Okay, Vg is again positive, because only when Vg is positive the holes will be repelled, and you can get into depletion and further inversion, right? How do we know it's inversion? Because EF at the surface is closer to, at the interface is closer to EC. In the bulk it's p type, but at the surface it's n type, so it's something called inversion. Second, and how will the, so second is inversion. How will the look like? Now what will happen is that electrons will start to accumulate here on this very thin region. Electrons will start to accumulate. Okay, just like holes were like accumulating, remember in accumulation. So electrons will start to congregate here, they'll start to come here, and you see this green sheet. This is for electrons, this is electrons. Depletion charge will still remain, the red block, but this electrons, they'll form a sheet of electrons here in inversion. So this is correct. In 3, so we see first of all that's an n-type semiconductor, because EF is closer to EC. And one other thing you notice is that what we have applied a positive bias. How do I know that? I know that because the bend that you see, EC, is now closer to EF at the interface, right? When will that happen? If you apply positive charge, the electrons from the bulk will get attracted, and the concentration of electrons has to increase. Just as I told you, just please remember this formula always, the ones which we wrote there, that n equal to nc exponential of EF minus EC over KT. So at the surface, EF minus EC gap is even lower. This quantity will rise, so concentration of electrons will rise at this. And when can they rise? If you apply positive potential here, so electrons will get attracted and they'll get accumulated. Again a sheet of charge will form. You see very small depletion region forming here, right? This, and how will the diagram look? Something look like this. This is a perfect capacitor. Remember, it's oxide here in the middle. We have a positive sheet charge here, negative sheet charge here, and this is what we've been habitual of seeing in a capacitor, plus q and minus q on opposite sides. So 3b is 3 will match with b. This is accumulation, the phenomena of accumulation. All right, so that explains the complete picture. And now let's just formally define some things, okay, before we move further into some problems. Okay, so a MOSCAP is said to be inversion when dash carrier concentration at the surface equal or exceeds the dash carrier concentration in the bulk. So we have to compare the carrier concentration at surface with the bulk. So again, this is a flat band diagram that we see. EF is the same. This is not drawn because that's an assumption that we've made. This EF metal and EF semiconductor. What do you do if you apply large enough positive bias? So holes will repel, you form your depletion region, and if the bias is large enough, the EF at the surface will move closer to EC and behave like an N type, while the bulk is still P type. So if you see at the interface, this interface, which we also known as, which we sometimes call as the surface, okay, at the surface, so minority concentration, this is a P type, so minority concentration, minority at surface has exceeded the majority in bulk. It has exceeded here. That is what we define as inversion. So this is the definition of inversion. The bias at which this happens, the minority concentration at surface is greater than the majority concentration in the bulk. So the correct option will be when minority concentration at the surface is equals or exceeds the majority. So this option, this one. Okay, while we are here, let me define some terms because we'll be using them again and again. There's something called phi f. How do we define phi f? Phi f is this difference, this distance. This is phi f. We haven't seen them in different and different devices that term differently, right? So EI minus EF in bulk, remember this is important. In bulk, intrinsic energy level minus Fermi level is phi F. What is phi S? S stands for surface here, right? So it's a difference between intrinsic energy levels. So in this case, for instance, phi S would be this much. This would be phi S. Not intrinsic at surface is here. Sorry, intrinsic of bulk is this. Let me redraw it. Sorry about that. So this is EI bulk, right? And this is EI surface. The difference between these two is phi S. Okay, this is how we're defining them. Now I have said that when increases at the surface, but there must be some other mathematical constructs that are there, right? Which we invoke in this problem. So here we know that in inversion the charge density will increase of minority charge carriers. But what is the relation? Okay, so on your right you can see the three regimes, right? We just saw them. We saw the accumulation, negative charge here, and you have a positive charge here, right? So in unless otherwise mentioned, we always talk about n MOSCAP. N MOSCAP will be realized on a p-type semiconductor because it will have electrons as inversion charge carriers. P-type will have holes in majority, the minority will be electrons. Hence, at the interface, if you apply large and a positive bias, electrons will be now deemed as the inversion charge carriers, and you can form something called an NMOS capacitor. This N comes from due to the electrons as inversion charge, but the substrate is p-type. Please note that. All right, so this we saw these three regimes: accumulation, depletion, and inversion. So depletion, you see there is no green charge of inversion electrons, right? Because the bias is still not high enough. But if you keep on increasing the bias from here to here, you see depletion is not increasing, but all the charge is being stored over here in green region, right? How do you denote this? We denote it something in this expression that you see here. So just look at these, only the accumulation first. All right, over here. So what we have, accumulation, we see is the, so as we increase the bias here, the positive bias we are increasing, or you see if you go to the negative side, you can see the accumulation increasing, which makes sense because you are attracting the holes, and hence this plus q charge. At zero nothing will happen. You have a flat band condition here. You see this flat band condition is marked here. Flat band is at 0 volts. If you increase, you will enter something called the depletion region, this regime. You see this word depletion here. Next, what's going to happen is that if you keep on increasing, there's something called the weak inversion. This means inversion will now start to happen. So at this point, it is intrinsic. At this bias, let's say at something at 0.3 volts, at the surface, it's intrinsic. If you keep on increasing it further, you will something called the weak inversion, and there is a point, right, where we just define the inversion, which is this strong inversion, where it happens and it rises exponentially, as you can see. In accumulation also it's exponential, right? Here it's not. Why it's not? Because if you recall, the expression for depletion width is dependent on the the depletion width goes as, if I recall correctly, as square root of built-in potential and all that. So those concepts are still invoked here. We are not going to details, but those are still present here when we talk about depletion region. But the key region of interests are the strong inversion, because here is something unique is happening. The semiconductor is p-type, but yet at surface it's behaving like an n-type, right? And this happens at strong inversion, and the and the increase in concentration after the strong inversion after this point will further define it in detail, rises exponentially. So the concentration of electrons after the inversion, and rather strong inversion, increases exponentially. We'll define what do we mean by strong inversion. All right, this is where we are defining it. So again, you see there are three regimes: inversion, depletion, and accumulation. We have seen them. So this is the flatband condition. So let's first apply a negative bias to it. Okay, and you see we are talking about ideal devices. So remember the first slide that we talked about today about ideal MOSCAP. So those will, like, insulator is perfect, the interface between semiconductor and oxide is perfect, and so on. Okay, so all those things still stand true here. Okay, so so on the, if you apply negative bias, you see like this. So what's going to happen, holes will get attracted, and you see EV and EF coming close, so holes concentration must increase. So negative bias, you must see accumulation. So this option is correct, this is correct. So on negative bias, you see accumulation. Fine. What happens, let's apply some positive bias. Positive has holes will be repelled, and you see, you can see some depletion happening. So negative charged ions will be left behind. Correct, we see something called the depletion. And if you increase the bias even further on positive side, that is, the bends will bend even further, and EF will move now closer to EC. Top band is EC, bottom is EV, and you see EF is closer to EC. That means surface, it's behaving like predominantly N type, while the bulk is still P type. Bulk is still EF is closer to EV. So this is called an inversion. So we see this, and you see this fellow 2 phi f. We just defined phi f. What was that? It was like this. EF was EI bulk minus EF bulk. So this was phi f. And what's, so how we are defining it is that, and then phi s is EI bulk minus EI surface. All right, this means that EF is below phi f, and this difference when also becomes phi f. Note here, this is EI surface, right, and here something is EI bulk. So difference becomes 2 phi f. This means the EF, which was by the same amount which was below the intrinsic level in the bulk, now has gone above the intrinsic level. This means, in other words, what we are saying is something like this, that the whole concentration in bulk, when it becomes equal to electron at surface, this is when we have what is defined as the strong inversion. This means now you can see bulk should be in majority, right, always, but since inversion is happening, when this becomes true, we see strong inversion has set in. Mathematically that happens to be at 2 phi f. Phi f we have already defined, something like this. Okay, so this is the phi s. So phi s, at phi s equal to 2 phi f, we have something called the strong inversion kicking in. And after that, if you increase, as we saw in the previous slide, like here, the concentration will keep on increasing exponentially, right? But we are only interested in the point at which it starts to happen, and we can always apply higher biases to drive more, to increase the electron concentration, and may drive higher current. Okay, and this point, when phi s becomes equal to 2 phi f, this means at the onset of strong inversion, let's say, this is formally also known as threshold voltage. So this term will come again and again when we talk about MOSFETs, metal-oxide-semiconductor field effect transistors. So the stack will remain the same, metal-oxide semiconductor, but we'll have two more terminals there. But this term threshold will come again and again. Hence, formally, we must define it strong inversion when phi s equal to 2 phi f. So this is again, so this is phi f. Okay, and this is also phi f. When this happens, what we'll have is phi s equal to 2 phi f, and we'll have strong inversion. And as I've told, that after strong inversion, it's an exponential increase in electrons. So this is the source link that you keep on seeing on your screen. I think this photograph is from Streetman and Banerjee, if I'm not mistaken, taken from textbook, because that photograph in the lecture slides was not very clear. So yeah, so that's that. All right, so we'll take a pause here because till now I've been talking about only basics of MOSCAP, the understanding the terms, what is phi f, what is phi s, what do we mean by accumulation, inversion, and so on, and surface potential. So I hope the terms are clear, but if not, just feel free to ask, because now I'll be using these terms very frequently when we solve some problems. All right. Okay, let's go ahead then. So okay, so now let's apply this understanding that we have to just get some electric field profiles. As we have seen in we did in p-n junctions, right? We draw some charge profiles, then electric field profiles, and then potential profiles. All these three are related. Electrostatics, if you recall your maybe 11 12 standard, or maybe also in your physics courses in your undergraduate first year, maybe second year, you must have talked about the electrostatics part of it, the Poisson's equation and Gauss law and all that, right? Charge, electric field, potential, they will always go in together. I'm not talking about time variation, just in space. Charge, electric field, potential. Here we do the same picture, just that we'll do it in case of a MOS capacitor. All right, let's do it step by step. Whenever you encounter such a problem, ask yourself, is this an ideal MOSCAP? So see in the question, is the question saying something about it? No. If the question is silent about it, just assume it to be ideal. Just assume. Okay. Next question you must ask, which region are we operating in? Remember, we had talked about 4 regions: flatband, accumulation, third will be your depletion, and then finally it's inversion, right? Okay, so those are the 4 regimes that we are operating in. So if you must recall, just sorry about that, which region are we operating in? You can see there's a negative charge that we have applied on the gate. Okay, and you see this is something called a depletion region. We saw that because if it were accumulation, so let me draw it in a different color. If this was accumulation, right, so you would see accumulation only at the interface, only here. So this was accumulation. It's definitely not flat band. Why it's not flat band? Because in ideal MOSCAP you don't see any charge in flat band, so it's not flat band. So I can say flat band, no. Accumulation, again no, because accumulation will have something like this here. Okay, something on the interface. It's not here, it's spread out in the semiconductor over a width w. It's depletion. Why it's depletion? Because you can see some depletion with w. Okay, so what, inversion also has some depletion width, but if it were inversion, then again there will be some charge here, which I'm drawing in red. So red stands for inversion charge. Again, you don't see anything like that here. There's no inversion, because the only charge that the problem is given is this blue sheet, which corresponds to depletion. So again, which region are we talking about? We are talking about depletion. So we identify that this semiconductor under the given bias is not flat band because there's some charge, not accumulation because then there'll be a thin sheet of charge. It's not there, it's spread out. It can be depletion because we see this, but and it cannot be inversion because inversion also has a thin sheet of charge. So the only option left is that this semiconductor is biased such that it is in depletion region, depletion regime, whichever you want to call it. All right, final question is asked, what is the type of this MOSCAP? I told you n type or p type. So we have to identify the substrate for that. All right, so you see the substrate has now the plus q, the background doping we have here is plus q. When does that happen? So when you dope it p type, let's say you dope it p type, if holes are left you will get Na negative, correct? If it's n type you get Nd positive. In this case it's a positive depletion charge. These are the your impurity charge. Okay, it's positive. This means the background must be n type, so it must be n type semiconductor, and I told you n type semiconductor would mean PMOS cap. So this device that is given is a is an n-type semiconductor, and thus it's a PMOSCAP, which is biased such that it's in depletion region. And you see it's a negative gate bias, negative Q, right? So we can clearly see Vg is less than 0. Now you can understand if Vg is less than 0, the holes will be the electrons will be repelled away, and a depletion region will be formed, which is seen in this blue slab here. All right, so we have established that much. Fine, good. But you are required to find the electric field plot now. So let's go step by step, as I told you. So in the first step, what is the electric field inside this metal node? There's a metal here, right? This here. Electric field inside metal, we know it's 0. Electric field inside the metal is 0. So actually it's not drawn here. Must be something like this, right? Okay, we have established that. But now we see as we go from metal, so what I'm going to do, I'm going to remove all the things that I've written near the diagram because I need some space. All right, so I'll remove all this. All right, so now from metal, now we talk about this interface, metal oxide interface. We have a negative Q charge here. So here again we invoke electrostatics, we invoke the boundary conditions at metal oxide interface. All right, so there are two things, parallel and perpendicular. So this direction I'm taking it to be parallel, this is perpendicular. This is the notation that I've been following. Okay, x-axis you can see is perpendicular, negative y is your parallel. So E parallel is 0 inside the metal, so this will become 0. So this is 0, this 0 field inside the metal, so this E parallel oxide will also come out to be 0. And you note that it's only given in x, so essentially we can just ignore the parallel because parallel means electric field in y. We are only interested in electric field in x. So from now we just forget about this parallel or the y dimension electric field, but we are interested in x direction. All right, again E perpendicular metal, right, which is in the x direction, is 0. Electric field inside metal is 0, right? So this will turn out to be 0. So 0 minus epsilon oxide Ex, or perpendicular, note this direction is x, okay, equal to sigma, the charge over here, correct, which is, let's say, minus q. So epsilon ox Ex oxide is minus q. Actually it should be q over some area, some cross section area. Don't worry about it, we just want to get a feel of it. So Ex oxide is going to be minus q over epsilon ox. Fine, we got some value, that's some non-zero field in oxide. What should be the direction? You can see it's negative, but that depends on the nomenclature. So let's try to figure out. If it's a negative charge, electric field should be towards it, correct? So electric field should be in the negative direction in oxide. So electric field line should travel something like this. So this is electric field lines. So electric field should be in the negative direction, right, which we can see it's coming here. Okay, so these two options are eliminated. Some constant electric field as a function of x, but negative, something like this. All right, okay, okay, now we have established that just at this interface, what is the electric field? It's this, just at this interface. Okay, so at this is at x equal to 0 only, not in the bulk of oxide, only at the interface of the oxide, mind you. Okay, what's the electric field inside oxide? Use this expression. Okay, this is from electrostatics, I'm not invoking anything that's not known to you. What's the charge inside the oxide? 0. Remember we said ideal MOSCAP, right? This means no charge traps or anything inside oxide. So this means delta dot E oxide as a function of x is 0. This means, or I can say that E oxide as a function of x is constant. So inside the oxide the field is constant. This is only at the interface, mind you, at interface. This analysis for interface, this analysis that you see on the bottom is for in the bulk of oxide. So this means what we get is, till now the picture that we get is something like this. All right, so this was actually not x equal to 0, this is actually minus T ox, because x equal to 0 is here. Let me draw this diagram now. How will it look like? Till now we have established inside the metal is 0, and from minus T ox to this thing, this is minus T ox, this is electric field E as a function of x. So in the oxide it's constant, right? Now we encounter this interface. Okay, now we encounter this interface, this one. So what we do, again we do the same analysis. Again, as I told you, just forget about this. We're not interested in y direction. Just ignore this for now. Okay, so as I told you, this is the parallel direction, this is the perpendicular direction, or the y and the x. Okay, so here we do this again. So this term we know, so epsilon oxide and E ox, which is a constant. Remember we had drawn that it should be, it's none of these options, so it was constant, some value here, minus epsilon of semiconductor times let's say Ex in semiconductor. This should be again equal to some charge, sigma. You don't see any charge here, surface charge that is, so this is equal to 0. Okay, so from here you get that E semiconductor at x equal to 0, mind you, again we are talking about only at this interface x equal to 0. This should be equal to epsilon oxide at x equal to 0 divided by epsilon silicon into epsilon oxide, just cross multiplication. So it's not is exactly equal to epsilon oxide. There is some factor that is there, epsilon oxide divided by epsilon s, right? So what we see is that we see a jump. It should not be the same, we must see a jump. So you see this option, so we have established there must be a jump here, and it's a negative, the sign does not change. All right, so now we have traveled up. What happens inside this? This is what we have seen, but we can solve this using this again, the same yeah, however you may, the Poisson's equation you can see, right, or the Gauss law, right? This is from your electrostatics expression that we have. So del dot E equal to rho by epsilon. So here we have a rho, right? This rho is coming, why? Because remember it was a MOSCAP. This means n-type semiconductor, which means it must have some ND doping, right? So this rho comes from there in the depletion charge. So again I can write it as del E semi, only 1D system, over del x. This should be equal to rho is something of this, so let's call this plus q over epsilon semiconductor, because we're interested in this region. So from here if you integrate, this is a constant by the way, correct? So if you integrate this, so you can see the slope is positive. Okay, let's call this some quantity m. So from this you can get E semiconductor equal to mx plus c. M must be positive. Okay, so we must get a straight line. M is known, c is not known, but you can find the value of c because from this boundary condition. Essentially you must get a straight line with positive slope. We get in this. So remember this was electric field is 0 inside metal. Then we see a jump due to this charge, interface charge. Then we see a flat line in oxide because there are no traps or charges hidden here, or the bulk charge. Then we see a jump due to this boundary condition over here, right? Due to difference in the dielectric constants, we see a jump, we see this, and then finally we solve this expression, and what we get is that inside semiconductor, inside the bulk of semiconductor, in the depletion region, we must get a straight line, y equal to mx plus c with m positive. So this is slope, and here naturally the field has to come to 0. Okay, because outside depletion region, so whatever charge minus q is here must be balanced with plus q, that is over here. So that is how we analyze the complete that is how we analyze a MOSCAP. Okay, I took some time, I went into very basics of it, But this is, if you at least if you do these three steps, what is the MOSCAP ideal, which region is operating in, what is the type of it, then rest of it becomes very simple. The rest, nothing new is happening. All of these things, you know the boundary conditions, you know their that their dielectric constants can be different, are different in fact. So these are the things that follow naturally after this. Okay, now as I have been telling, if there's electric field, this potential, so this is the charge that is given. Right now we need to plot the potential. So we already know how the electric field profile looks like from previous problem, right? What are we going to do? We're just simply going to do E equal to minus grad V. All right, so if you, this means we have to integrate this, so, or you can write it V equal to minus E dx. That's it. So integrate this. So here there's nothing, correct? There is something, remember this negative charge, something we have applied a minus Vg over here at this metal interface. Hence you see, you must start with the negative potential. They must, if you integrate this, you will get a constant plus C, right? That C, the starting point here must be some negative minus Vg at this interface. Okay, and so integration of a flat line is a slope line because E is constant here, we just saw previously. So in oxide, V must be directly proportional to X. Simple, because negative negative will get cancelled, so V must be directly proportional to X. In semiconductor, V must be directly proportional to X square. Why? Because E, you see, E is directly proportional to X, so V must be directly proportional to X square, because here E equal to constant. And why this? Because E equal to, E is a function of X. Just a second. Okay, so that's what, so what we'll do is that, so here you start with some negative potential, then it must be a straight line. So in oxide it must be a straight line, so this cannot be true, this cannot be true. It's a positive sloping straight line, so actually this is the option. Here you must get a quadratic X squared, something like that. Okay, since we start with negative potential, so this potential you can see is minus Vg. Okay, remember this was biased and depletion. Okay, so we are applying some potential to gate. This is that potential, some reference which we are taking it here. Okay, yeah, so that's about it. This we talked about a PMOS cap. Until I've been telling you that nothing is given, it's usually NMOS, but this problem I took it just to illustrate you, because last session we talked about that same concepts are valid in PMOS. I just said it. This time we are just solving it, that this, all the concepts are indeed valid in PMOS cap. Just that you just follow the flow, that's it. Okay, now we'll do a similar problem using the same concepts or the approach that we have been talking about. Okay, so here the question says electric field profiles for an ideal MOSCAP are shown. So there are two MOSCAPs A and B, their electric field profiles are shown. We need to find the MOS device, whether it's PMOS or NMOS. Okay, so as always, is it ideal MOSCAP? Well, yes, the question itself says so, so nothing to assume here. Question is very clear here, but if nothing, we'll assume. Second, which region? Okay, again I'll do the same thing. Please recall in the previous problem, right? So what I told you was that flat band it cannot be, because for flat band what's going to happen is that the charge profiles look something like this, and then this. So this is your oxide, this is your oxide. Let's say here there'll be no electric field. This is the bulk of semiconductor, this is semiconductor, this is metal. In the bulk of semiconductor there is no electric field, but here you can definitely see electric field existing. Flat band, no electric field even exists, so flat band cannot be there. Okay, what about accumulation? Accumulation, so sorry, I made the diagram wrong, sorry, let me just. So in flat band you see no charge at all, because it's an ideal MOSCAP. So the no charge means no electric field, there's no charge here, so this is Q, there's no charge anywhere. Okay, so there's no electric field, so this is, but there is electric field, this cannot be flat band. In accumulation, what happens is, this is metal oxide semiconductor. Let's say there is some sheet charge here, and there will be again a sheet charge here, correct? These two sheet charges. There will be nothing in the bulk, but we see the electric field in the bulk, which is not true for accumulation. Accumulation, the only electric field exists is that is in the oxide, nothing in the semiconductor. But we see a finite semiconductor field. This depletion with W, we are clearly seeing this cannot be accumulation either. So either is depletion or inversion. We don't know which yet. Okay, but it has to be depletion or inversion. Fine, we get that it's either depletion or inversion. Which one, we'll have to figure out later. For instance, A can be in depletion or vice versa, B is inversion, but both are not in flatband or accumulation. The third question which I have been proposing that you ask yourself, what is the type of the MOSCAP? Okay, so it's actually very easy to do in this case once we know it's in depletion. Or you can compare with the previous problem. How? When it was a PMOS cap, right, the electric field was in the negative direction. Remember, this was a PMOS cap. PMOS cap, electric field was in the negative direction. Why negative direction? Because you applied a negative gate voltage. This was a negative charge here, and to balance it, there was some positive depletion charge, right? So all the electric field profile was in the negative direction, correct? Here we see electric field on the positive side. When can that happen? The polarity has changed. Very simple, very logical explanation. MOSCAP type is NMOSCAP. But what if you don't remember which one is which? Then you can simply, again, we can do that. How? Assume it to be in depletion. Assume this device is in depletion. So in depletion, okay, so let's draw the diagram for NMOSCAP. So NMOSCAP is mean this is on a p-type semiconductor. So this is a p-type semiconductor, right? If it's depleted, right, if it's depleted, it must have Na minus S charge. This is a bulk charge, Na minus. That means to balance it, it must have a positive sheet charge over here. This is metal, this is oxide, this is semiconductor. See, electrically it has to be, the balance has to be a capacitor. Opposite plates which should have opposite charges. So if this is positive, if this is negative, that is, which it must be because the p-type semiconductor depleted, this must be positive. So when will it have positive charge? When Vg, or the potential that you apply on the metal, is positive. So when you apply a positive potential, the holes will get repelled away, you will form a depletion region. When do you have excess holes? When it's a p-type substrate. P-type substrate means NMOS cap. So both of them have the similar profile, both of them electric field in the positive direction, right? Hence both of them are NMOS, this option. Because this is positive charge field lines are away, so field lines will be in this direction in oxide. Okay, so if field lines in this direction, they are positive, this is positive X. That's how we determine. So the three problems which I suggest you follow, you solve them. Ideal MOSCAP, in depletion or inversion, and it's an NMOS capacitor. Very good. The second question asked is that which one is it? Depletion, inversion, accumulation. We've already established it's not accumulation. So let's forget about this. Let's find out which mode is it. All right. So again, just now only look at this interface. The one second. Sorry, the metal oxide interface. So I want you to look here. It says metal here. This is oxide. At the metal oxide interface, we again follow this parallel and perpendicular. Again, I told you to ignore this because we are only interested in the x direction. So let's ignore this. All right. Okay. So let me ignore that and let's concentrate only on the x direction, that is. All right. So what's going to happen here is, so let's see. So let me write it for A and B. So for A, I am writing this. So E metal will be 0 for both, right? So what I can write is epsilon oxide 1 A rather, right? And E oxide A is equal to some sigma A. The metal charge will be here. So remember, the profile will look, charge profile will look something like this. This is metal, you'll have some charge here. This is oxide, and there is some depletion that's happening here, W, for both. Okay, so this is your oxide, this is your semiconductor, this is your metal. This is charge profile I have drawn here. Okay, so this is the sheet charge that I'm talking about, sigma A. Similarly, I can write epsilon ox B, electric field in oxide of B, equal to sigma B. Assume that the oxide is the same for both. All right, so what I'm going to divide them, these two expressions. So I'll get E ox A divided by E ox B equal to sigma A by sigma B. This charge, this is the charge I'm talking about, sigma, either it's A or B, so different. Okay, so we know that for A, electric field is higher, right? So I can simply say sigma A by sigma B is greater than 1, because this entity you see from these values, red is higher than blue. So sigma A is greater than, or I can write sigma A is greater than sigma B. When will that happen? That can happen when you have a higher gate bias, because this is charge here. This charge will come here only when you apply a higher gate bias for A, right? And note that B is also depleted, A is also depleted. In depletion, so remember, when you are depleted, if depleted, we may enter inversion. If bias is increased, depletion width does not increase. Note that between A and B, the depletion width for both of them is the same, W. What's happening is that whatever charge is, so this picture that you see, so for A, what's going to happen is that for A, you will also see a charge accumulating here because it has entered inversion. This is for A. This is for A. For B, the picture will only have the depletion charge. Okay. Hence, so since A will have the depletion charge as well as this inversion charge, so the balancing charge on the metal has to be higher. It can only be higher if there is an inversion charge here, right? Depletion charge is the same for both of them. Why sigma A will be higher? It can be only when A has entered depletion. So we have to say that since sigma A is greater than sigma B, that tells us that, and depletion width the same. Note, if the depletion width are different, then we cannot make this argument. But depletion width the same as for both of them, A and B. This means A and B are equally depleted, and yet A has more charge. How is it possible? Only it's possible only if A has some inversion charge. So we have to say that A corresponds to inversion, while B corresponds to depletion. Depletion is true for both, but A has entered inversion. Okay, right? So now what they are asking is something we have already talked about. We're talking about, we have to identify why this discontinuity is here. So we saw that. Remember this boundary condition oxide semiconductor interface. Again, you just ignore the parallel thing or the y direction. Okay, this is the thing that we got. So why is there a jump? The jump is there that just assume for the case of B. So I'll write this for B. For B, epsilon oxide E oxide should be equal to epsilon semiconductor E semiconductor, correct? Because it's in depletion, no inversion charge. No inversion charge. So sigma is 0 here, sigma here I mean. Okay, so why will there be a jump? So you can see we saw this epsilon's electric field in silicon will be electric field in oxide times epsilon oxide by epsilon silicon. Same direction, the sign remains the same, only the magnitude changes. Hence you see this jump. So we see a jump at discontinuity at the interfaces due to the permittivities of SiO2 and silicon. So this is true, correct? Second statement, difference due to difference in semiconductor and metal work function. No, remember we had talked about an ideal MOSCAP. An ideal MOSCAP, the EFs are the same, correct? And work function is defined as that the energy difference between your Fermi level and your vacuum level. If the Fermi level is the same for metal as well as semiconductor, your work function is also the same. So S2 is in fact incorrect. There's no difference. They're exactly the same. Statement 3 asks, the jump is higher in B due to presence of charge carriers at the interface. Is higher in A, sorry. We already established that A has entered inversion. A has entered inversion, right? So A will also have this for B it was 0. For A this will also be present, right? So the difference, right, will be even higher. That's what it's saying. Okay, so what we'll have is, so this is also true. S1 is true, S3 is 2, and S2 is false. So this is the correct option, this one. All right, let me summarize what we did here. So given this statement, we first assumed it to be an ideal MOSCAP, which was given in fact in this problem. Secondly, we tried to establish which regime is it in: accumulation, depletion, inversion. We saw there's some depletion region in the semiconductor. That electric field means there must be some charge in the bulk of semiconductor. That means it cannot be accumulation and it cannot be flatband. So depletion has to be there, or inversion. And then finally, since we saw that electric field is in the positive x direction, we established it's an NMOSCAP. It's a p-type semiconductor, thus an NMOSCAP. Finally, we established that A is in inversion, B is depletion. Why? Because both have the same depletion width, but A has higher electric field. That is possible only when, we saw here, that is possible only when A has some inversion charge also. Inversion charge arises only when we have inversion. So we established that, and then finally we analyzed the jump in discontinuities here, which attributed to the fact that this difference in the permittivities. So that's complete analysis of your electric field profiles. Obviously voltage profiles can also come, but that's secondary. You can just integrate them, as we, if you recall that we had done some problem for PMOSCAP, that this is, or E equal to minus grad V. Just use this expression, or V equal to minus E dx. Okay, just use them and you can get your voltage profiles also. Just remember here gate is positively biased, so here the voltage profiles will entirely be above the x-axis. Okay, so in the PMOSCAP it was entirely below the x-axis, because for depletion or inversion rather, because we applied a negative gate bias. So that's the only difference. The analysis will remain the same. The key thing that I want you to take away from this is that first, just by looking at the electric field profiles or by looking at the charge profiles, just analyze whether it's in accumulation, depletion, or inversion, firstly. Secondly, what type of semiconductor it is, or what type of MOSCAP it is rather. Okay, if you do those things, then rest is just very easy. This is just one formula you have to remember, the boundary condition, and this is something from electrostatics, not even from core semiconductor physics, let's say. All right, so just to summarize what we had talked about, and then we'll take a pause so that you can gather your thoughts. If you want me to repeat something, I can do that. So here the question asks, the external applied gate voltage VG in a MOS structure will drop. So where is the VGA consumed? So remember, this is the same diagram from the PMOSCAP that we had. So this was a negative gate bias, we had applied minus VG some here on the metal, and then we had some depletion in the semiconductor. So this was your PMOSCAP. How do I identify PMOSCAP? Because it's a positive depletion charge. Positive depletion charge means ND plus. ND plus means donor. Donor means N-type. N-type substrate means PMOS. Then we saw these electric field profiles. Finally, we saw this, the voltage that we saw, right? If you see, this is the voltage VG that I was talking about, the magnitude. Some of it is dropping here. Let's call this Vox. Some of it is dropping here. We call this V built in. Again, I told you can't run away from built in. There's depletion, there has to be built in voltage. There's charge, there's electric field, there has to be potential, right? So in other words, I can simply say that, that VG, okay, I have to be careful, the magnitude of VG, right, has to be equal to magnitude of Vox and magnitude of built-in voltage. just that. All right, note that there cannot be any current flowing, because please remember, this is oxide, it's perfect oxide, it's perfect insulator, it has does not have any, does not permit the transport of any current, right? So so just be careful with that. All right, and as you know that EF we have been drawing is constant throughout. If you recall, I'll go to some, okay, we'll maybe ahead. EF we have been drawing perfectly flat, like for this problem EF is flat even though there is some gate voltage, right? There's no transport of carriers. Fine. So we saw that the VG is being dropping in oxide as well as in semiconductor. This is oxide. Some potential is dropping here, some potential is dropping here. So we write partly across the oxide and partly across the semiconductor. Right. This again you will say that this will happen only when it's in depletion mode or inversion mode. Yes, correct. In accumulation this will not happen. Okay, in accumulation, because the whole charge will be just at the periphery of your oxide, so all the potential there in accumulation mode will drop across the oxide. True, that is true. So there must be this is conditions apply. All right, finally, just to summarize, so whatever we have talked about till now, a MOS capacitor can be represented as, so if you, sorry, if we recall that we had done this is oxide, here we have a metal, and here we have our semiconductor, right? So what we are seeing is that this is perfect capacitor, right? Because it's one plate is metal, second plate can be here, it's accumulation, it will be a perfect one. But otherwise we saw in the depletion region, just like in the previous problem, you see here, so you see one field is dropping here, electric field is here as well as here, or see the potential, some potential is dropping here, some is dropping here. So what's the capacitance? So let's call this Cox for corresponding to this let's call this C semiconductor. They are in series. Remember, the second plate has to be somewhere. Let me draw the charge profile, then it will be easier to understand. Let's say you are applying some positive bias, so this is the charge profile, this is your metal oxide semiconductor, your charge profile, and let's say you have depleted, and let's say you also formed an inversion charge. So this is some plus q, this is some minus qn, this will be your na minus. Okay, this is your oxide, so no charges will be there in the oxide. What do you have here? So just focus on the oxide. So oxide has this plus q on one side, minus qn on the other side. So this is a capacitor. So let me model this. Let's write it something like this. Correct? This is first plate, this is second plate. Here also, this is there, right? There's some charge here. I can also write this as the capacitor. But if it's not fully depleted, this is dependent on gate bias. Correct? So this capacitor, this is constant at Cox. This is variable. Whether it's fully depleted, half depleted, or even entered inversion, this will depend on Vg, the gate bias that you are applying over here. Here you are applying some gate bias, some potential Vg. So what we see, it's in series. So two parallel plate capacitors in series. One is fixed, Cox, you cannot change. Cox will be epsilon area, which is cross-sectional area, they're not showing here, divided by Tox. You cannot change these parameters. One constant, and the other one will depend on Vg, so it's controlled by voltage, and they are in series. This one constant, which is Cox, one voltage controlled, which is Cs, in series. You can see they are in series. All right, that's a summary. So a complex device like a MOS capacitor can be modeled just by a very simple two capacitances in series. This is a very handy tool when you actually want to analyze it, put in some circuit, let's say some RC circuit. can use this if some problem appears. All right, so till now what we have been talking about is the understanding of that how the charge profile looks like in a MOS capacitor when you apply different biases, identifying which mode is it in, depletion, inversion, accumulation, analyzing the electric field profiles and the corresponding voltage profiles for that matter. Right, we had done all that. Now let's go to some lighter problems. Right, what do we mean? We'll solve some numericals. That's what I mean. Okay, so I have this problem. The energy band diagram of a MOSCAP device is sketched in the figure below. Assume that the electrostatic potential is 0 in the semiconductor bulk. They have defined the bulk, that is at large distance from SiSiO2 interface. So bulk is somewhere over here, large distance from this interface. Okay, and there is no metal semiconductor work function difference. So essentially they are defining an ideal MOSCAP. These all whatever it's happening is the your ideal MOSCAP. Okay, and assume the relative dielectric constant of the oxide to be 3.9. Rest of the things are given to us which we might want to utilize. So what is the value of phi f? That's the first question. So if you recall, phi f we had defined it as something like this: ei bulk minus ef of bulk. So bulk, it's been defined at large distance from SiSiO2 interface. So this means, let me define that the bulk is this region on the right to the dashed line. All right, so in the bulk I try to identify ei, which is this level, ef bulk, which is this level, the red line, the difference between the two. So you can clearly see is that ei bulk is lower than your ef bulk. So this will be minus 0.42 ev. This is 0.4. ef is higher, so this must be a ef is higher than ei, hence this whole quantity will be negative. So phi f is minus 0.42 ev. Options are given in volts, so essentially this is not, they're not talking in terms of energy but voltage. So you just drop the e, electronic charge, here. So what we get is that phi f is minus 0.42 volts. Fine, we have done that, but let's first just analyze the system a bit, try to understand the system a bit more. First we see is that ec is closer to ef. This means it's an n-type bulk semiconductor. Okay, it's an n-type bulk semiconductor. That's good. What's happening is that I'm also seeing a finite depletion width, w. Okay, this means that this device is not in accumulation, definitely not in flatband. You can see, because ef, you can ef of metal is over here, correct? Ef of semiconductor is over here. You can see clearly a difference. It's definitely not flatband. Is it accumulation? No, because you see a finite depletion width. In accumulation you don't see any depletion widths. It's all the charge that is there. In this case it will be electrons, because it's n-type, will be accumulated here, correct? It definitely depleted. How? Because you're applying a positive gate bias, sorry, a negative gate bias. A negative gate bias will appear as positive energy because the electronic charge is negative. Okay, so if you apply this, then what will happen is that the electrons will get repelled away from this, and thus what will be left behind are the positive donor ions, Nd plus, which will form the depletion region, which you see over here. Okay, from illustrative purposes I'm just drawing these donor ions. Okay, we do not know whether it has entered inversion or not, but it's definitely depleted. So that much information we have right now. So let's proceed further now. Now you obtain phi f is minus 0.42. Now it asks what is the surface potential phi s. So surface, by surface we mean here. Okay, please note this is what we are referring to as at the surface. All right, and please note it's a p MOSCAP because the substrate is n-type. Okay, so what is the surface potential phi s? So we have an expression of phi s that is given ei bulk minus ei at the surface. Okay, ei bulk minus ei surface. So let me just first choose a different pen. Okay. So what you can see is that the bending is 0.3 EV. This means that EI must also have bent 0.3 EV. EI is just your midpoint of EC, and if EC bent 0.3, then EV must also bend 0.3, and thus EI must also bend 0.3. So from bulk to surface, right, this is the definition: EI bulk minus EI surface. So EI bulk is over here, correct? EI surface, this is but nothing but EI surface. This value is EI surface. This is EI bulk. So you can see that EI surface is higher by 0.3 EV than EI bulk. So I can write it as minus 0.3 EV. EI surface is higher. EI surface is over here. We extend this. Write it again. So this is EI surface, and this is EI bulk. EI surface is higher by 0.3 EV than EI bulk, hence the negative sign. So we get it as 0.3. Again, the electron E sign is the electronic charge is taught because we are expressing in terms of potential, okay, volts, not expressing in terms of energies. Okay, fine. The next question asks, what is the applied voltage VG? Now remember some previous questions which we had solved. The gate voltage, we saw the gate voltage will drop if in accumulation it will drop only across oxide, because I told you that in accumulation it will be something like this. So metal oxide, this is the metal, so let's say some charge is here, and in oxide, so this will be here, and so this is metal oxide semiconductor, right? In accumulation, something, a picture like this would emerge. So the whole, all of the electric field will be inside the oxide, and thus all the voltage drop will be in the oxide. But otherwise, if it's not in accumulation or flat band, you will invariably see some depletion region, which we are definitely seeing here. So the gate voltage that we are applying will drop in oxide as well as in the semiconductor. Okay, this is for only for accumulation. In the corner that you see, but here we definitely see a depletion width. Okay, all right. So I was saying, yeah, the applied gate voltage, what will happen to that? Sorry. So VG, what is the value of VG? It's just the height from the Fermi level. Right? Remember, in flat band, when there's no gate voltage applied, both EF as well as EF metal are at the same level. Here they are not. This shift of 0.96, so it has to be 0.96 volts. I get that. Which sign is the problem? Again, I analyze it. I prefer to analyze it rather through which mode I am in. So remember, this is a N-type semiconductor and a PMOS. These two go hand in hand always. Okay, so and we know we are depleted. So when can you deplete an N-type semiconductor? You can deplete an N-type semiconductor only when you apply a negative bias at the gate, because the electrons will then be repelled away with the electric field of this metal voltage that you are applying. So for N-type semiconductor to be depleted, negative bias must be applied to metal. So this VG, whose magnitude is 0.96, must be negative. right? We have already established, mind you, we are in depletion mode. Okay, we are in depletion. I don't know about inversion. We are definitely in depletion. Inversion cannot come without depletion, so we are definitely in depletion, maybe inversion, but depletion has to come, and hence this voltage has to be minus 0.96 volts. Okay, again the E is dropped because we are talking in terms of potential, not the energies. Okay, what is the voltage across the oxide? So we have already seen this. I told you Vg must be equal to Vox plus phi s. What is this phi s? Remember this. What is this drop? Different names, but we saw it's something called the built-in potential. So this is the drop. This is the difference between the levels of EC at the interface, or the surface that we've been calling this at the surface, or the semiconductor oxide interface, from the bulk, something called similar to concept called VBI. This is 0.3. What is VG? VG is minus 0.96. Note, already done that. Vox, we don't know. Plus phi s. What is phi s? Phi s is minus 0.3. So Vox will turn out to be minus 0.66 volts. This one. Now again you might get confused with the sign. Just understand that if you are applying 0.96 total, 0.3 is going here, the rest of it is being eaten up by the oxide. Okay, total bias of 0.96, total, let's say, energy of 0.96 EV applied, 0.3 EV is being consumed by the semiconductor, rest of it will have to be consumed by the will have to be dropped in the oxide. Now again, what charge? Again, just this is an n-type semiconductor. In order to deplete, you will have to apply negative potential, so all the potentials will be on the only on the bottom of x-axis. So if I were to draw the potential profile of this semiconductor, let's draw this. Okay, how will it look like? Let me attempt. So it will look something, so this is your x-axis. Here it's negative, minus 0.96, minus 0.96. Then we saw it must increase linearly. Why? Because electric field is constant in an oxide, right? And then finally it will go something like this. This is your potential profile. Potential as a function of x, 0.96 volts, and this point is your minus 0.3. Very bad scaling, but you'll get the idea. So this drop, this straight line drop that you see, is minus 0.66 volts, right? Okay, let's move further. We are asked to find the doping density in the bulk. So again, the bulk, please remember, is to the right of your depletion region. So this is the bulk, and we had already established its n-type, because in the bulk EC is closer, EF is closer to EC as compared to EI. Okay, let's do that. How do we find the ND? We already know the value of we already know the EF, the value of EF corresponding to EC, so, or corresponding to EI, either one will be fine. There is a slight error, it's EF minus EI. So n equal to Na exponential of EF minus EI over KT. Just refer to, I think, your second or third week of lectures. So N, this is electron concentration. Again, I'll assume full ionization. We had solved some problems. What is the value of N? N will be equal to Nd. Assume complete ionization. So at room temperature, usually, since KT is given as 26 milli-electron volts, this corresponds to T equal to 300 Kelvin. At room temperature, and this is electron, by the way, 1.1 eV and 10 to the power 10 cm minus 3. It's silicon. In silicon, usually at room temperature, your impurities are ionized. So electron concentration, so all the donors would have donated their electrons, hence N can be written as equal to Nd. Ni is our intrinsic concentration, which is 10 to the power 10 exponential of EF minus EI. So EF minus EI, so that is already given as 0.42 EV EV divided by KT, which is 26 MeV. So I just have to solve this out. So this will be 0.4, this will be 420 by 26. So let me find my calculator, just give me a minute. It will be exponential of 420 by 26. Okay, this is a big number, let me divide it by 3, 4, 5, 6. So it's coming out to be 1.04 into 10 to the power 17. This is 10 to the power 10, this is 1.04 into 10 to the power 7. This is Cm minus 3 because Ni was Cm minus 3. So this is, okay, we have to round it off also. This is approximately 10 to the power 17 and 1 into 10 to the power 17 Cm minus 3, this option. Okay, so we'll have so 1 into 10 to the power 17. Let me just check one more thing. Remember we had talked about non-degenerate semiconductors. All the expressions of n equal to Ni and Nc, Nv, whatever was valid only for non-degenerate. That is when Ec minus Ef, this difference, has to be greater than 3 kT. So let's just try to find out if it's true or not. So we have time, so we can do this exercise. So Ec minus Ef, I can write this as Ec minus Ei minus Ei minus Ef. So Ec minus Ei is nothing but half the band gap, so this will be 0.55, and sorry, this will be Ef minus Ei. Yeah, Ef minus Ei. Ef minus Ei is given as 0.42, so this will turn out to be 0.13 EV, and 3 kT will be 0.078 EV because 3 times 26 MeV. So you can see that 0.13 is greater than 0.078 EV. So we are fine. This is not a non-degenerate semiconductor. Sorry, this is a non-degenerate semiconductor. So this expression is valid. Valid. We are good. Another thing is that 10 to the power 17 is slightly, is, you can say it's, we are fine with that. But if we made it 10 to the power 18, okay, then we might get dangerously close to this 3 kT figure. All right, it's a good check to do this, especially for your some exams like gate and maybe in some university exams, multiple choice questions. This can be a, you can just lose marks just by not checking this. It's a good practice. If you have time, I recommend to do this. All right, so we identified that this n-type bulk semiconductor is doped with 10 to the power 17 Cm minus 3 dopant atoms. Okay, finally we are required to find the width of depletion region, W. So this W, remember I've been saying that this has been depleted, right? And I've also been saying that we are applying some Vg equal to minus 0.96 volts, so around 1 volts of negative bias we are applying to deplete this semiconductor. What is the width? The width, this expression is again from your PN junctions, so it used to be VBI here. Okay, and I have been saying that this is the bend that we are seeing. The bend in the EC, we used to call it as built-in potential, correct? Here we just calling with a different name, phi s. From a how should I say this? From a mathematical perspective, the relation between W and this, the bending, it does not matter what you call it. The only matters is that is the physics behind it the same? Yes. So whatever name you call it, built-in potential, surface potential, it's going to remain the same, right? So just put the numbers here. So epsilon naught is 8.85 10 to the power minus 14, because remember we are doing it in percent, in centimeter, not in meters. Epsilon s, this is for silicon, so silicon is 11.8. Phi s was given to us as 0.3. We have to put the magnitude here, not this sign. So just Q is 1.6 10 to the power minus 19. Sorry, yeah, Q is 1.6 10 to the power minus 19, and ND we found out as 10 to the power 17. So units will be centimeter here, please note, not meters but centimeters. Let me again try to find out what this is. 2 into 8.85 into 11.8 into 0.3 divided by 1.6. This is 39, and so square root of 39 would be 6.25. 6.25. Power would be 14 here, and it would be minus 2. Yeah, so 14, 10 to the power minus 12, so 10 to the power minus 16, minus 6, sorry, 10 to the power minus 6 centimeters. So if we have to do it in nanometers, so this will be 6.25 into 10 to the power minus 8 meters. This will be 62.5 nanometers. Yeah, 62.5 nanometers. This one. Remember, we have entered nanometers. If you recall your PN junction, I had once recommended that just have an estimate in your head that what are these typical values that you usually obtain from these devices. Here we have entered in nanometers. There, if I recall, was hundreds of nanometers or maybe a few microns. I remember one problem where we once depleted the whole N region. There, that was I think around 4 microns, right? Here we are talking about only tens of nanometers, 62 nanometers, correct? I don't think I have one more problem, but there was one more problem, I am forgetting that. So it was something like this, that what is the typical width of oxides that we use in semiconductor manufacturing. This means this. Okay, so this has gone to very low values, in some cases single digits of nanometers. So when that happens, there's some effects, tunneling can happen, and there are some many other non-idealities that come in. I'm not going into that, but I just want you to but the point that I want to emphasize here is that we are now, in your handsets, we have devices which are in nanometer regime, and we cannot go much further down because the lattice constants few angstroms. Okay, for 5 layers you hit 5 to 6 layers, you will invariably hit a nanometer. Okay, and we are operating in that as only few layers of materials, right? Of the standard materials I'm talking about. Novel materials can have higher thicknesses and other peculiar properties. What I mean to say here is that the ideal world that we are studying or analyzing here, right, when you actually try to design that or even fabricate that, it's a non-idealities do come into the picture very big, in a very big way. Hence you must have at least an understanding that what range we are, these values will give these numbers, and how to get those numbers. So this is a very simplistic picture where this problem was designed just so that you can approach the problem. First find out phi f, which is dependent on doping density. The doping density is something you can control, right? And thus you can control phi f. If you control phi f, and Vg is also in your control to an extent, right? If you control Vg, then you can control the surface potential. And with the thickness of oxide, use different oxides, the voltage dropping there, you can have more voltage dropping in the semiconductor, less voltage dropping, and the depletion widths. So those are the variables that you can control. Sorry, the variables nd and nd to an extent is in your hands. Vg, some control you have, and rest of the things you have to play which values you want to get. So that's that the takeaway that I want you to have from this 6 problems from 4 to 9 that we discussed. All right, so what I'll do is that we have 15 more minutes. So I'll take a pause here because the next set of problems builds on the understanding. We'll not have any numericals to solve there, but whatever understanding that we have. So my arguments will be, it's like electric field look like this, the charge will look like this, and so on. All right, so before we go into more analysis right? I'll if you have any doubts, want me to repeat something, just please feel free to ask. I'll be more than happy to do so. All right, if not, then let's just get into the last set of problems for today. So let's read the problem first. A graduate student X fabricates a semiconductor oxide semiconductor capacitor, SOS capacitor. Till now we have been talking about MOS capacitor. So on the left side also, yeah.
Sir, in previous question, electron concentration and doping concentration both are same.
Electron concentration in the bulk. Okay, this analysis I am done only in bulk.
So it was doping concentration was 1 into 10 raised to 17 per centimeter cube. So
Yes.
that was the electron concentration, or it should be different.
No, that's what I'm saying. See, since we are operating KT equal to 26 MeV, okay, if you put the value of Boltzmann constant here, the temperature around comes out to be 300 Kelvin. This means this device is sitting at 300 Kelvin room temperature. At 300 Kelvin, usually, and this is a silicon because we have been given Eg as 1.1 eV, Ni is given 10 to the power 10 again at 300 Kelvin, and the dielectric constant is 11.8. All these things indicate, and plus it's also written here, I should have made this point, this is silicon that's been given to us. Okay, in silicon usually the dopants that we introduce are fully ionized at room temperature. That's an assumption that I'm making, and it's a good assumption. I want you to just go back to that. I'm forgetting, it's third session or fourth session. We had talked about this in multiple problems where repeatedly emphasized that at 300 Kelvin you can just simply assume that all the impurities that have been added, all the dopants that have been added to the silicon semiconductor, they are fully ionized. That means if you are adding 10 to the power 17 cm minus 3 of dopants, each of them has given one electron at room temperature, that is at 300 Kelvin, and thus the electron concentration in the bulk will be exactly equal to Nd, the dopant concentration, because each dopant has given one electron. Okay, that analysis is true only at 300 Kelvin. Let's say if this temperature was 4 Kelvin, okay, at 4 Kelvin, very few amount of dopants would have given their electrons. So there the electron concentration will be most likely, so N at 4 Kelvin will be very close, I believe, to the intrinsic, not even intrinsic. So intrinsic will also be not 10 to the power 10, because this intrinsic is at room temperature. Note, intrinsic concentration also depend on the temperature. So this will be very close to intrinsic, because very few of the dopants would be ionized, and only background concentration will be that of intrinsic, and maybe there will be some ionization at 4 Kelvin. At 0 Kelvin there will be nothing. So what I'm trying to say is that since we are moving at we are talking at room temperature, so if you just hold on a second, what I mean to say is something like this. So if you recall, on the y-axis we have the electron concentration N, on x-axis we have the temperature. Okay, so this is in log scale, concentration is in log scale. So what happens is that, let's say let's mark some temperatures, 100, 200, 300, and somewhere over here let's say 700. So what happens is that below 100 or 50 degrees the concentration increases. In log scale is increasing linearly, this means increasing exponentially, then it flatlines, something like this. And I'm forgetting the temperature, drawing is really bad, just give me a second. So at around 100 Kelvin, let's say, all the dopants have ionized, so the concentration will remain flat. Intrinsic will keep on increasing, but it's very low. However, at high temperatures all the dopants have given their electrons, and now the concentration will be due to the intrinsic one. This will again be exponential. So this is exponential increase, This is flat line because intrinsic concentration is still very low. So let's say this is 10 to the power 17. Okay, so 10 to the power 70, intrinsic is much lower. So almost all the contribution is coming from your dopants, and we are talking about 300 Kelvin. So we are here. So what I am assuming is that at 300 Kelvin all the dopants have ionized, and thus the electron concentration is equal to the dopant concentration. If we are talking about 700 Kelvin, right, then what would have happened, that intrinsic concentration would itself has increased. So there maybe the doping concentration will not be that much contribution to the total electron concentration. Does that answer your question?
Thank you, sir.
Yeah. All right. That was a good doubt. Okay. So now we are talking about now SOS capacitor. So just you can clearly see on the left side is a semiconductor, not a metal. Okay. It says that SOS capacitor differs from a MOS capacitor due to the fact that semiconductor gate may be biased in accumulation, depletion, or inversion depending on the applied voltage. So remember, when we had metal gate, we always had a sheet charge here, right? There was no depletion, inversion, but it was the same polarity as the voltage. If you apply positive potential to the metal gate, you always had a positive sheet charge here. For semiconductor, the case can be different, right? So here it says that, so the structure looks something like this. We have an oxide and we have an n-type semiconductor on both sides. It's been given n-type silicon electrode, so left and right both. First is your let's say flat band. You can see the bands are flat. So what's happening here? Nothing will happen. There's just like in the flat band in the MOS capacitor, and assuming everything else remains ideal, right? No traps, nothing like, no non-idealities. There's no source. I mean, the EF is the same on both sides, and the electrons cannot travel through this oxide. It's a perfect oxide. So no charge can be. So there will be no charge. So for the first problem, this means when Vg equal to 0, flat band condition. What's going to happen? This means this diagram 1 will match with C. There will be no depletion, accumulation, nothing like that. No electric field is there. Nothing is being transported. This is perfect n-type bulk. On the right side, perfect n-type bulk. So first will match with C. Okay, 1 will match with C. Nothing is happening at all. Boring. Okay. Now, next it asks, you apply a small gate bias. Small, remember, small. So let's say Vg equal to 0.1 volts maybe. Okay, let's see what happens. That for that to understand, just for the time being, just assume this to be a metal gate. I just want to see the effect of if you have a metal gate with positive bias, what is the impact here? So let's just try to draw that. So what I mean to say is that this is your metal gate, right? This is your oxide, metal, oxide, and this side you have your semiconductor, and I apply a positive bias, a small positive bias. What will happen here? Metal is positive, right? So what's going to happen? This is an n-type. It will attract the electrons. It will cause accumulation. So how will the charge profile look like here? Let's draw that also. So metal is positive bias, so this positive sheet charge will be here. It's metal, oxide, and inside semiconductor the electrons would have been accumulated here. This is charge. So what I'm drawing here is Q versus position. Okay, so that's how it will look like. It's accumulation. I expect of a similar nature, I expect things of the similar nature to happen here. Not same, remember, similar. Okay, so what by that what I mean is that I am expecting that an accumulation of electrons to happen in this side. This side will obviously play a role because in metal none of the voltage was dropping. Note, the voltage was constant. Remember an assumption, equipotential metal. There was in the ideal MOSCAP we had this equipotential metal, right? But the voltage can drop in semiconductor, but the trend I expect to be the same. This means the accumulation on the right semiconductor. All right, expect that to happen, but how will it will it happen, will it not happen? Let's see. So this is the diagram that we have applied a positive bias on this. How do I know that? The electron, this band has shifted, EF levels are not the same. EF has shifted a bit towards the downside here. So remember, because this is an electron energy we are talking about, if you have a positive bias, the bend will shift a bit down. Okay, so bend the electron, sorry, the energy bands have shifted a bit towards the lower side here. You can see that this is higher, this is lower. So what's going to happen, you can understand many things are going to happen, because the EF is higher here and lower here, so electrons will tend to come to this side. They cannot, this is perfect insulator, but still, so the electrons will accumulate on this edge. All right, just like this, right? Electrons will try to accumulate on this edge. So what we can see, I am expecting an accumulation over here as well. What's happening here? Remember, you have applied a positive bias here on this interface, positive bias, and this is an n-type semiconductor. So what's going to happen, this positive bias, this